Since time immemorial, humankind has looked to the stars. The universe has always been a source of fascination and of mystery. How was the cosmos born? What else might the universe contain? And where do we come from? We are surrounded by an intangible infinity, a universe in which the Earth is merely a grain of sand on the shore of an ocean. But we are unravelling more and more of the secrets of the universe which surround us. And that includes black holes, bottomless pits like the jaws of hell, which devour all material that comes close to them. Even light has no chance of escaping from them. But how does a black hole form? Are there any near us? And can they pose a threat to us? Welcome to Spacetime, featuring astronaut and scientist Ulrich Walter and an expert on surprises the universe has in store for us. A look at the universe presents us with pictures of fascinating and confusing beauty. Landscapes of light and gas and stardust, formed by cosmic wind and radiation. Our telescopes are discovering more and more wonders of the universe. They are looking far out into space and thus far back into the past.
We live in a universe that is truly fantastic, and today we're going to take a journey to a fantastic place, the center of our Milky Way, where an enormous black hole lurks. We will also encounter other fantastic phenomena. But be warned, it could cost us our lives.
The center of our galaxy is marked by a super-heavy black hole, an astronomical object with an inconceivable gravitational pull. Nothing can escape from it.
Can you believe that in our Milky Way, the galaxy in which we live, there's a black hole? A black hole that really does devour everything? That's precisely the case. How do we actually know that? Because fortunately, we have space telescopes out there. The picture you see here, for instance, was taken by Chandra, an X-ray telescope. And if you look very closely at the center of our Milky Way, you can see individual stars. They are the bright dots, and they move. This movement appears to be chaotic. But it isn't. These stars move on precisely defined paths, known as Kepler orbits. Astronomers have studied these orbits for many years and discovered that they are in fact ellipses. The blue lines you can see here. In fact, you can see lots of blue lines. This means that a vast number of stars are moving here. And if we focus on just one star, let's take this one here, you can see that at this point it makes a very fast upwards movement. This tells us that at this specific point there must be a giant mass. And this mass can be calculated. In this case, it's 2.8 million solar masses, and precisely that is our black hole. Because its mass is so dense, there's nothing that can escape from this black hole, not even light. And if no light can be emitted from this region, obviously we can't see anything. That's why a black hole is black. The characteristics of a black hole are fairly dependent on its size. Whether it's one solar mass or millions of solar masses, what often happens is this. Somewhere there's a white dwarf, as it's known, with another large star circling it. This star pushes some of its mass down onto the white dwarf. When this mass reaches the white dwarf, at first it orbits the star, emitting a huge amount of light. But ultimately it falls into the white dwarf. It's like a small droplet causing a large barrel to explode, because this white dwarf really does detonate in a massive explosion, leaving behind a black hole. All that can be seen from the outside is what we call a planetary nebula, and it looks beautiful. So how big are black holes? Well, all black black holes are formed by large stars which explode. That's why there are several million black holes in our Milky Way. But as we just saw, those located exactly at the center can gorge themselves, so to speak. Whole masses, entire stars, fall into these black holes, causing them to swell to huge objects of up to 4 million solar masses. And that's why we have such a huge one at the center of our Milky Way.
The black hole at the center of our galaxy is known as Sagittarius A-star. Of enormous size, it devours everything while remaining totally invisible.
A black hole is a point in space which contains so much material that the force of gravity is incredibly powerful, so powerful that not even light can escape from it.
Only a few decades ago, black holes were a purely theoretical concept.
The notion that if I cannot see something, I can't really prove its existence isn't quite true. When we observe the stars at the center of our galaxy, we are seeing stars that are moving around one area, the way the planets move around the sun in our solar system. In this case, the focal point they are circling cannot be seen. From the movement of the stars, however, it's possible to calculate the size of the mass at the center of their orbit.
Astronomers' keenest eyes are in outer space, like the Hubble Space Telescope. Black holes cannot be observed directly, but they exert a distinct influence on their environment. Astronomers and astrophysicists can monitor and evaluate these effects.
Black holes differ considerably. Some are roughly as heavy as our sun, or maybe 10 times heavier. These black holes are formed at the end of a star's life. Through it we call a supernova explosion. A star releases a huge amount of material, which we see as an explosion. At the center, a black hole is left, which usually has a mass of 5 or 10 suns.
The corpse of a star, infinitely small, compressed to nothing.
But there is also another, totally different type of black hole, one that is found at the center of galaxies, like our own Milky Way. These black holes weigh millions or even billions of solar masses.
The black hole at the center of our Milky Way is a special cosmic feature, but it is not the product of chance.
Scientists today even suspect that there is a supermassive black hole at the center of every galaxy, which possibly even stabilizes the galaxy.
Black holes stir our imagination and that of Hollywood producers. The journey to a black hole is a departure to one of the frontiers of our knowledge.
As we have seen, a black hole exerts a gigantic pull. But how can that be? To answer that question, we have to think a little bit like Einstein. Imagine that our universe is a two-dimensional space, like a tabletop on which we place a rubber mat. Next, we put a huge mass on this rubber mat in the form of a large ball. It represents the sun. The force of gravity from this mass causes the space to bend. Space here is represented by the rubber mat, which, as you see, has expanded. If we now bring the Earth into this curved space, this is the Earth. The gravitational force is nothing other than the perceived curvature of space in the direction of the funnel. I'll sketch it in. This is the gravitation, and as you see, this is the increase in the curvature. But the Earth doesn't simply topple in. Imagine there's a marble rolling on the tabletop. Its initial movement, say, is in this direction. The marble then moves in a circle on this curved tabletop. At each point on its orbit, the marble feels gravitational forces pulling it inwards. Those are these gravitational forces that now point inwards. Thus, we have movement, which is nothing other than movement in this curved space. By the way, it's not only space that's curved. Along with space, time is also curved. That's why we talk of curved or bent space-time. In reality, things are even more complicated. Space isn't two-dimensional, it's three-dimensional. You have to imagine this space-time compression not just on one plane, but in all directions. So the Earth can orbit the Sun not just in one direction, but in every possible direction. So let's now imagine that the Sun isn't the Sun, but a black hole. In other words, millions of solar masses. It's then clear, of course, that the curvature of space is massive. The curvature of space, and thus the gravitational force, is so massive that it points directly downwards. So if I now introduce a mass here, this mass will plunge straight in, and it has no chance whatsoever of getting out again. And this force, this curvature of space, is so enormous that a photon, which I'm going to draw right now, this being the photon, sees this force. So why can a photon, a light particle, see this force? A photon has energy according to E equals mc squared. This corresponds to a mass, and it is precisely this equivalent mass that is affected by the force of gravity. In other words, the curvature of space. Even a photon will orbit this black hole at some time or other, and also fall into it. Photons, light particles, fall into the black hole because of the curvature of space, and that's why a black hole is pitch black.
It is the most compact form of matter. We could not imagine anything more compact. Sagittarius A-star was discovered in 1974 with the help of a radio telescope, but it was not until the early 90s, after many years of observation, that astronomers succeeded in proving the existence of a black hole at the center of our Milky Way.
I draw conclusions about the black hole by observing matter that is located around it, to see what it's doing there, what kind of orbits exist there. I can then measure how heavy the black hole is at the center.
In 2011, astronomers discovered a gas cloud moving towards the black hole at the center of our Milky Way. They named the cloud G2. Scientists waited tensely to see whether the cloud would be devoured, but it survived the flyby in 2014.
We discovered a gas cloud, and you can see wonderfully well how this object falls around the black hole. However, it isn't a star, which is compact, but a ragged gas cloud. What we notice is that this gas cloud is stretched by the black hole. These are tidal forces, exactly the same forces that produce the tides on Earth. Here we have a differential force. The effect is more powerful at the front than at the back. This results in objects being pulled apart.
Black holes are gravitational monsters which suck in everything around them. Nevertheless, the threat to us humans is more than minute. We live in a backyard of the cosmos, far away from the nearest black hole.
There are not really any black holes in our vicinity, so they don't pose any major threat to Earth.
Gazing into space is one of humankind's primeval experiences. Cosmic distances are almost inconceivable for us.
Our black hole is at the center of the Milky Way, 26,000 light-years away, and thousands of years away in a current-day spacecraft. Just think of it, 26,000 light-years. Even if we could travel at 10% of the speed of light, it would take us 260,000 years to get there.
But even if we could travel through space at the full speed of light, the journey would still take 2,600 years, the time span from the early Celts to our age of information. Over 100 generations would have to be born and die on a spaceship traveling at the speed of light before it finally reached its destination. And if we traveled at only a fraction of the speed of light, we find ourselves on a virtually endless journey through black nothingness.
Such a journey would be relatively unspectacular for the first, let's say, 25,999 light-years. It would just be boring. But near the black hole, things would suddenly start to get exciting. Near the event horizon, of course, the passage of time would change. Here, space-time, as it is known, changes considerably. Someone looking from the outside would get the feeling that they were never going to reach the event horizon. In other words, to get close to the black hole.
The most distant object in space humans have visited so far is the Moon, a tiny step into the vastness of the universe. So could a human being ever bridge the distance to a black hole?
The distance from the Earth to the black hole, in other words, to the center of our Milky Way, is around 30,000 light years. So from here, light would take 30,000 years to get there. We know of no rocket technology that could manage that in a reasonable time. But imagine we did have a rocket that could travel at the speed of light. How long would it take? Well, we'd need 30,000 years to get there. And now comes a really important point. In a famous publication in 1905, Einstein showed that when we travel at almost the speed of light, space and time expand, just like with gravitation. In other words, I wouldn't need 30,000 years to get to the black hole. For me, the time would be shorter, maybe just 10 or 20 years, so I could fly to the black hole within my lifetime. Isn't that great? And now, imagine that I would fly back again, so I'd need another 20 years. And imagine I had a twin brother. When I left Earth, he was maybe 20 years old, the same as me. I would get back after 40 years, so now I'm 60. And what has my twin brother experienced? Think about it. 30,000 years there, 30,000 back. According to his time, that's 60,000 years. He would be long dead. So what has really happened is that I have made a journey to the Earth's future. That's the significance of Einstein's special theory of relativity. It allows travel in time, into the future.
So any interstellar journey would not only be a journey through space, but also through time. Humans on their way to the center of the galaxy would be space-time travelers. However, Albert Einstein's theory of relativity does not permit a journey back into the past. Quasars are among the brightest objects in the universe, and every quasar has a super-heavy black hole at its center.
When we look for a black hole, we're looking for something with a huge appetite, something that devours a great deal. When material tumbles into a black hole, it heats up so much that it shines very brightly, more brilliantly, in fact, than an entire galaxy. These objects are called quasars, from quasi-stellar or almost star-shaped. Seen through a telescope, they are very bright, dot-like centers of galaxies.
Like lighthouses, quasars mark fixed points in the endlessness of space.
Quasars are galaxy cores that shine very brightly. So they are specific and important points in the universe. I'd almost describe them as beacons. To us, they appear as no more than dots because they are so far away that we cannot fly to them. Basically, though, a quasar is something that marks a certain spot, and it can actually serve as a form of orientation.
When you discover a quasar, you have found a black hole. But there are some black holes that do not emit any radiation, so they remain totally invisible.
In one case, it depends on whether the black hole is getting something to eat at that particular moment you're looking for it. The other way is to search for the force of gravity, and that, of course, is the more systematic approach. The force of gravity is always present. So when you see the force of gravity of a black hole, you have definitely identified one.
But especially when a black hole is devouring matter, it leaves clear traces, which scientists can identify and evaluate.
You have a stellar black hole, and next to it, for example, a red giant. Part of the red giant is drawn into the black hole, creating what we call X-ray flares. So this hot material falls into the black hole, and in a very short time, hours or even minutes, it becomes incredibly bright, and that can be seen.
1999, launch of the Space Shuttle Columbia. On board, the X-ray telescope Chandra, a time machine. The telescope looks deep into the universe's past. It registers the radiation which quasars emitted over 10 billion years ago and observes the behavior of black holes. Chandra is still providing pictures of stars that explode and collapse to become black holes. In 2012, NASA placed another eye in space in the form of X-ray telescope NuSTAR. With a definition 10 times greater than that of Chandra, NuSTAR is designed to search space for sources of X-rays and, in doing so, make a systematic inventory of the black holes in space. We are living in a golden age of astronomy. Scientists find themselves on a seemingly never-ending voyage of discovery to the frontiers of our universe and beyond. It is also a journey to the frontiers of our knowledge in our search for the blueprint of the cosmos, and we are gaining new insights at shorter and shorter intervals. But there are still no answers to the question of what happens inside a black hole. It is a mystery that has been puzzling physicists for decades. We want to satisfy our curiosity and see with our own eyes. So we are now setting out for the black hole at the center of our Milky Way. It is a mind game. The distance doesn't matter, nor does the duration of our journey. Our explorers are following the gravitational lines in space. But what awaits them at the edge of the matter-gulping abyss? And what phenomena will they encounter on their journey through the universe?
One really exciting question is, what would really happen if you flew in a spaceship almost at the speed of light and looked out? Would the stars still look like spheres? After all, the stars are spherical objects, as are the planets. Would they still appear as spheres? The surprising answer is yes, because of the theory of relativity. If the theory of relativity did not exist, when we flashed past a star, what we saw would look like a cigar. We would see elongated shapes. But because of the theory of relativity, if we looked out, we would only see spheres. If we pass our sun at almost the speed of light, we would see a beautiful sphere. So our dear Lord perhaps prepared us for space travel, because the theory of relativity ensures that spheres stay spheres. The only problem, of course, is that when we move at high speed, our field of vision becomes steadily restricted. Suddenly, light seems to come solely from the front. And the faster we fly, the narrower our field of vision gets. This can also be demonstrated with simulators. In the end, I can only see what's in front of me. That, so to speak, is the point when I'm traveling at almost the speed of light. I can only look forward and see the world basically as it comes toward me.
In science fiction films, space travelers not only feel acceleration, they see it as well.
These Star Wars animations are fantastic. They show stars all becoming lines or dashes because the spaceships fly at warp speed. But I don't think that is the way it is.
There would not be any direct view on a flight to our galaxy because the spaceship would have to be massively armored.
Then there would also be the problem of everything being subject to Doppler displacement. In other words, the light which is emitted and is perhaps optical infrared light suddenly shifts into the X-ray and gamma range. Then I would not be able to see anything, either because I would very quickly be dead, or I would be blocking my own view in order to protect myself from the gamma radiation.
In his general theory of relativity, Albert Einstein said that gravitation bends space. Thus, even rays of light are diverted. Light is bent around a body. The body just has to be heavy enough.
So large masses, in particular, that means black holes can bend rays. That's hard to get our heads around. How can rays be bent? But it really is possible. And there are some truly bizarre examples of that, the most famous being the Hubble smiley. Let's take a look at it. What we see here is a Hubble photograph. You can make out the various dots, and each of these dots is an entire galaxy. So each dot contains around 100 billion stars. And here you can see a face, 2 eyes, 2 galaxies, a nose galaxy. But this ring, isn't a galaxy. We'll see in a second what it is. And out here, this circle is the outline of the face. The decisive point in this picture, however, is this little dot which you can see in the middle. It's a fairly large galaxy, but one that is a really long way off. It has a truly gigantic mass. Even further away behind the galaxy is a star. Light from it travels past this galaxy and is bent to such a degree that we see these circles here. This effect is known as gravitational lensing. To get a better understanding of this, we need to look at the entire picture from the side. Now the same situation, but zoomed in on this little galaxy which now appears as a large galaxy. You can see it here, and at the center is a black hole, indicated by this cross. So what happens? Well, in the background we have this star. We as observers are roughly here. So we are looking across the black hole and the galaxy towards the star. What can we see? Well, the star is emitting its light. But this light is not passing the galaxy in a straight line, but is bent towards our eye, in every direction. In other words, if I take another direction around here, it again bends towards our eye. You now have to imagine that three-dimensionally. What do our eyes do? What are they seeing? We think that the ray of light is coming in a straight line from this point, or conversely, from this point. But since, in fact, all rays are traveling circularly around the galaxy, it looks as if there's a ring around this entire galaxy.
As described in the relativity theory, light moves on bent space-time. The phenomenon that becomes visible is known as an Einstein ring.
Could this effect also be used to see isolated black holes? After all, we know that there must be millions of them in our Milky Way. Basically, the answer is yes. Then there would be no bright point of light at this spot, just a bare black hole. And we would only see a ring like this. That would be a clear indication of an isolated black hole.
The closer we get to the black hole at the center of our galaxy, the greater the effect of its gravitation on us. We enter a world of bent space and curved time. While our spaceship is moving towards the event horizon, for us on board, time is passing quite normally. Gravitation is having the same effect on us as it has on our environment. But the time in which we are moving is expanding more and more. Seconds become years and then centuries. We don't see the black hole, but we feel it.
Since light is never emitted from a black hole, I would never see it. I would only ever feel the black hole through the gravitation which it exerts on me. In that respect, I wouldn't have anything particular to fear.
Insofern hätte ich jetzt hier nichts Besonderes zu befürchten. Ich würde natürlich
I would, of course, always expect to see a star here. After all, I am measuring gravitation. I am flying towards something which exerts a force of gravity, but is simply as black as the rest of space. If we could really see a black hole, we would presumably see a large black shadow. The best portrayal of that was in a film which appeared in cinemas some time ago. A large black hole was shown in the film Interstellar. In fact, the large black hole audiences saw was created by scientists. They determined what it would look like. It wasn't left to the imagination of some director. To design it, physicists applied the theory of relativity. You see a shadow, and around this shadow, there is a relatively bright ring of light. That, so to speak, is the light which is deflected around the shadow and then reaches you. The black hole bends the space around it, which acts like a lens. So what you get is this lens effect.
Black holes take our powers of imagination to their limits, but physics can explain every phenomenon up to the event horizon.
Every black hole exerts gravitational force. It's the same with our sun. If we flew to the sun and instead of moving around it on an orbit, simply switched off the engine and stationed ourselves in front of the sun would grab hold of us, and we would hurtle into it. The same with a black hole. If I place myself in front of a black hole, switch off the engine, my speed would be 0. Then it would pull me in, and at some time or other, I would be behind the event horizon and be gone. With the sun, there is no event horizon. There would just maybe be a small flame as I burned up. But in the end, there would be no difference.
Radiation exits a black hole at the speed of light and is invisible to the naked eye.
But if I had X-ray eyes or radio eyes, things would be totally different. Suddenly, everything would be totally bright. From close to a black hole, I would probably be able to observe radio jets and radio nodes being emitted.
In orbit around a black hole, we would encounter another phenomenon.
Let's assume I'm at the distance of a photon sphere from a black hole and fly around it. If I now emitted light forwards, it would travel around the black hole in a closed orbit. I would see the back of my own head the whole time. That would be really amusing.
That is only one of the bizarre effects that await us in the intangible depths of the universe.
In the meantime, we've entered orbit around this sphere. And what do we see? Well, when we look out, we see that the light is coming towards us. We would also see the masses falling into this black hole. Everything has become bluish. This is known as a Doppler displacement, or a blue shift, because the incident light gains energy, and this shifts it into the blue range. So things out there look rather unreal. We're starting to fly very quickly and are approaching the speed of light, but we are still in a stable orbit. In other words, we don't need to do anything. We're flying in a circle around this black hole. But now we have to watch out. When we approach to within 30 million kilometers, our orbit becomes unstable. A bit closer, and we would automatically fly into the black hole. We can only keep ourselves out by thrusting against the gravitational pull. 20 million kilometers out, and we would be powerless to stop ourselves flying into the black hole, never to be seen again. But that's not the case with light. Even at a distance of 20 million kilometers, light can still escape from the black holes. That's why we can still see something. But when the photons, the particles of light, have reached the event horizon, there's nothing they can do either. They orbit the black hole, and when they get closer, fall into it. And that's the reason why, with this event horizon, no photon can get out. We can no longer see anything, and that's why we have this black sphere in front of us.
For every black hole, there is a point from which there is no way back. It is the boundary at which nothingness begins.
The only distance from a black hole that can be defined is the event horizon, the curtain, so to speak. Up to that point, the world is in order. And beyond that, no one can say because a black hole conceals all information from me. Anyone who fell in could shout for all they were worth. If they were behind the event horizon, I wouldn't hear them.
Lost in space and time.
If you find yourself behind the event horizon, you are gone. Completely. You can't see from the outside, and you can't look out. No one can say what happens to the matter which is sucked in by black holes. As a physicist, you would say, it is gone. The information you had beforehand is also gone. This worries physicists, because that should not be the case. It contravenes certain fundamental laws of physics. Something must have happened to the matter, but our theories do not tell us what.
The event horizon, a border zone at which it would seem all life ends.
Life always means that there is structure which preserves itself. But perhaps in the final analysis, gravity is, after all, one huge grinder which destroys every structure. And gravity is more powerful in a black hole than all other forces. So I'd regard the chances of any form of life existing in a black hole as extremely slim.
One of the biggest hindrances to traveling through the universe are the astronomical distances involved. But Albert Einstein's theory of relativity could provide a solution. It offers an, albeit theoretical, shortcut.
If black holes bend space and time, couldn't that fact be used to create a wormhole? What is a wormhole exactly? Let's take a look. Let's imagine a three-dimensional space portrayed once again as a flat surface. We place a large mass in it. You can see that here, a black hole. For the time being, we can forget about the lower part. Then we again have this funnel. So here, space is bent as far as the black hole. And now Einstein says the following can happen. If this black hole is nearby and on the other side of a universe, which is also three-dimensional, we have here a flat surface. This black hole would also create a curvature, a funnel on the other side. So we would have a black hole and on the other side a white hole. But why black and white? Well, the black side would cause all matter, like a spaceship, to fall in here. A white hole would do exactly the opposite. It would spit this mass out again. In other words, the mass would fall in here and come out again on the other side. So it's clear that through a wormhole, a spaceship could end up in a totally different part of the universe. Einstein himself said that wormholes could exist. The question is, do they really? Unfortunately, we have not seen any sign of this anywhere in the universe. Another totally different question is, would it be at all possible to fly through these things? Could they be used as a shortcut to get from one part of space to another? The simple answer is no, they couldn't. That would never work. Why not? Well, imagine a spaceship flying into this black space. The hole would go zip because it's dynamically unstable. The lower part would separate from the upper part, leaving only the black hole. The spaceship would be trapped, and that would be that.
But a wormhole would be an easy way of saving a lot of distance and time.
A wormhole would be a shortcut through this curved space. Imagine if you have an apple and a worm crawling over the skin. As it moves from the top of the apple to the bottom along the outer surface, at some point or other the worm will arrive. Of course, it would get there much faster if it could go through the middle of the apple. This is the shortcut the worm would take. The surface of the apple, however, is two-dimensional, and the worm would have to munch its way through a third dimension. Take things a dimension higher, which is not something our brain is equipped for. Unfortunately, it's only designed for three-dimensional space. But this, roughly, is how we can envisage a wormhole. It's a shortcut in three-dimensional space. Theoretically, the general theory of relativity says this is possible. But wormholes would only be stable if there were a certain form of matter which we have not yet found evidence of. Only then would the openings of these wormholes, so to speak, really be stable. And no one has found proof of these anywhere in the universe. So experimental evidence that these wormholes exists is still lacking. If they did, that of course would be fantastic. The gigantic distances in the universe could be covered very quickly.
Consequently, Hollywood also makes use of wormholes to make travel through our universe possible. And in search of the meaning of the origin of life, physics doesn't come into it.
A journey into a wormhole could prove pretty dangerous. You would need a very stable spaceship because in this case, too, space-time would have to be bent open to an extreme degree. Bending space-time involves powerful gravitational forces over quite a short distance, and they could tear me apart. I need a very robust spaceship.
But wormholes are just a theory of astrophysics.
At present, nothing like that exists, but we can imagine it. Such ideas are acceptable. But at no point in the universe is there any indication that wormholes exist.
The James Webb Space Telescope will be a new celestial spy. It will hover above the Earth at a distance of 1.5 million kilometers. The telescope is the most expensive measuring instrument ever built. A cooperation of NASA, ESA, the European Space Agency, and the Canadian Aerospace Authority. Comprised of 18 segments, its main reflector has a diameter of 6.5 meters. A shield the size of a tennis court will protect the telescope from the sun's rays. On an orbit 1.5 million kilometers from the Earth, the telescope will take the deepest look so far into the endless reaches of the universe. Only in space will the telescope unfold to its full size. The James Webb Telescope is designed to peer into the very origins of our universe, studying the genesis of stars and galaxies and determining the role played in the universe by black holes. But it is with an observatory on Earth that scientists have opened a new window on space. Through it, they observed the collision of two black holes, the two monsters of gravitation, one with a mass of 29 suns, the other with one of 36 suns, cannoned into each other and fused to form a single black hole. The energy that was released shook space-time. For the first time, physicists were able to measure the vibrations from such a collision.
And what a collision it was. Two large black holes came close to each other, and in the end, they fused. These were two very heavy objects, which were also moving very fast. A lot of gravitational waves were generated, and these gravitational waves were registered on Earth.
Albert Einstein had predicted the existence of such gravitational waves, but it was only a century later that science was able to prove their existence. It was on September the 14th, 2015, that gravitational waves were detected by a special observatory in the United States.
Imagine, for example, that a gravitational wave was going to hit us. Space would start to oscillate. And with the help of lasers, I could then measure how the distance between two places has changed. But that's very difficult because this effect is incredibly minute. We're talking about first being able to measure a distance of 10 to the power of 22 meters over several kilometers.
The gravitational waves crossed a distance of 1.3 billion light-years before they reached us. Distortions in the structure of space and time. Gravitational wave astronomy promises a totally new view of the universe.
Gravitation waves are the heralds of gravity. It is rather like me throwing a stone into a pond. Then I see waves on the water, and that is how you can imagine gravitational waves.
Their discovery was a sensation.
The importance is totally fundamental. It is just as Einstein predicted. In the past, their existence could only be proved indirectly. Direct proof was lacking. So from a fundamental, not just an astronomical point of view, and also from the point of view of physics, it is highly important that this has been discovered.
These observations will also help us to better understand black holes.
Vermutlich sind es auch die schwarzen Löcher, die in den Zentren von den Galaxien sitzen.
The black holes located at the centers of galaxies regulate how much matter comes in and the degree to which stars in a galaxy can form.
Das heißt also, dieses schwarze Loch ist
This also means that a black hole is something of a feedback for stellar genesis in galaxies. In other words, black holes could regulate the formation of stars in the universe.
Sternentstehungsgeschichte im Universum.
Proof of gravity waves is another stepping stone along the path to knowledge. Up to now, only light and radio waves could be observed, and most of the cosmos doesn't emit any radiation at all. Yet gravity has an effect everywhere.
It shows that our theories are correct, that Einstein was actually right, that the laws of nature which we have must be valid.
Sagittarius A-star. The supermassive black hole at the center of our Milky Way is about 26,000 light-years away. But scientists suspect that numerous smaller black holes are far closer to us. Meanwhile, our Earth quietly continues to trace its orbit in the solar system.
Here on Earth, we have no reason to be afraid. I think that what is alleged to take place in the LHC, that tiny black holes would be created, so it shouldn't be switched on, is absolute nonsense.
The LHC is the most powerful particle accelerator in the world. Here, protons are fired at one another at the speed of light. When the machine was started up for the first time in 2008, skeptics feared that the end of the world was nigh. Today, the accelerator runs at twice the original speed and still hasn't generated any black holes.
What takes place in the LHC happens every second in the atmosphere. And if black holes really were to form in the LHC, that would also happen all the time in the atmosphere. But we're still here, it seems.
If black holes could be created with the LHC, we wouldn't need to travel to the center of our galaxy.
Is it actually worth making a journey to the black hole at the center of our Milky Way? If you ask me, I would do it at once, and for two reasons. If we flew there, we would experience Einsteinian reality. We would see gravitational lensing. We would perhaps travel past a black hole or a wormhole, but we'd have to be careful not to fly into it, otherwise we would never get out alive. Imagine having a black hole in front of you, being the first human to see a real black hole. What a thrill that would be, but I wouldn't fly into it, otherwise I too would be a goner. I'd first fly around the black hole twice, maybe, and then return straight to Earth. And now comes the second important point. By the time I got back to Earth, 60,000 years would have passed on our planet. I would have made a genuine time journey into the future of humankind. What could be better than that?
Mysterious black holes. We are discovering more and more of them in our universe. Some of their fascinating secrets can even be deciphered. But as always, here too, science's explorers are only just setting out.